Today we're going to talk about simplifying, multiplying, and dividing radical expressions. So these are those expressions that involve a radical symbol, or you might see it look like that. The first thing we're going to do is simplify radicals, or non-perfect square or cube roots. So what I like to do in example number 1, I'm finding the square root of 32, and I want to break it down in its most simple form, or simplest form. And the first thing I'm going to do is find the biggest perfect square that goes into 32 a whole number of times. So 32 is divisible by that perfect square. And the biggest perfect square that goes into 32 is 16. 16 times what is 32? 2. So I rewrite the square root of 32 like this. The square root of 16 times the square root of 2. This might be a good opportunity if you don't know your perfect squares, and this is an Algebra 2 lesson, so you saw this probably in Algebra 1, and you might have seen it in geometry as well, is to have a perfect square chart, okay, that just tells you, hey, 1 squared is 1, 2 squared is 4, 3 squared is 9, and so on and so forth. And I like those to usually go up to maybe 25. So the square root of 16 times the square root of 2. And what I'm going to do is rewrite that perfect square. What is the square root of 16? It's 4. So I'm going to rewrite this. That's 4 times the square root of 2, which I will then write as 4 times the square root of 2, or 4 square roots of 2, or 4 root 2. You might hear any one of those versions. So now let's move on to the square root of 56, number 2, the square root of 56. What's the biggest perfect square that goes into 56? It's just 4. 4 times what is 56? 4 times 14. So I'm going to rewrite the square root of 56 as the square root of 4 times the square root of 14. So, and I can rewrite, like, there's not a bigger perfect square that goes into 56 because 14, there's not a perfect square that goes into 14, right? The only factors of 14 are 1 and 14 and 2 and 7. Those are the only numbers that go into 14. So I know that 4 is the biggest perfect square that goes into 56. So what is the square root of 4? It's 2. So I'm going to rewrite this as 2 times the square root of 14, or 2 root 14, or 2 square roots of 14. So now let's move on to examples 3 and 4. We're simplifying cubed roots. So just like square roots, for example, the square root of 4 would be, if I can break 4 down into 2 times 2, and if I have 2 of something, I can pull 1 out. Okay, that's kind of the best little way to visually show you this. If I'm looking for something like the cubed root of 8, now I need 3 of something to pull out. So 8 breaks down into 2 times 2 times 2. So now if I have 3 of something, I can pull 1 out. So now let's look at how to do the cube root of 135, or how to simplify it in its most simple form. So let me erase this. And let's move on. Lots of erasing, lots of erasing. And let's change colors here just because I want to. So the cube root of 135. So what I like to do is, let's do some dividing. 135, well, 1 plus 3 is 4. 4 plus 5 is 9. 9 is divisible by 3. That's one of those divisibility rules. So if it's divisible by 3, when you add up each of the digits, and that number is divisible by 3, then that number is divisible by 3. So 135 is divisible by 3. So I'm going to divide it by 3. 3 times what is 135? 3 times 45. Well, 4 plus 5 is 9. 9 is divisible by 3, so I can divide it by 3 again. How many times does 3 go into 45? Or what is 45 divided by 3? It's 15. And again, we have a number that is divisible by 3. 15 divided by 3 is 5. So I'm actually going to show you visually. The cube root of 135 is like the cube root of 3 times 3 times 3 times 5. And if you have 3 of something, you can pull 1 out. So I can rewrite this in its most simple form, in its simplest form, as 3 times the cube root of 5. And that's what that would be. Let's move on to number 4, the cube root of 56. 56 is even, so I know it's divisible by 2. I'm just doing the prime factorization of these numbers, right? So these are all prime numbers, so that's why it's the prime factorization. So 56 divided by 2 is 28. Another even number, so I know it's divisible by 2. 28 divided by 2 is 14. Another even number, so I know it's divisible by 2. 14 divided by 2 is 7. So I can rewrite the cube root of 56 as 2 times 2 times 2 times 7. And again, if you have 3 of something, you can pull 1 out. So this simplifies to 2 times the cube root of 7, right? Because that 7 is left under there because I don't have enough to pull 1 out. I would need 2 more 7s, and I don't have two more 7s. So 2 cube roots of 7, or 2 times the cube root of 7. Let's move on to number 5. So number 5, this is an example where we have variables involved, and they're raised to exponents. So what I first want to review is if I have something like the square root of x squared, that's the square root of x times x. And if you have 2 of something, you can pull 1 out, right? Well, what if I have the square root of x cubed? Well, that looks like this, the square root of x times x times x. Okay, well, I have 2 of something, so I can pull 1 out, but I have 1 left over. So I would rewrite the square root of x cubed as x root x, or x times the square root of x. So that's really important to whenever you're simplifying these square roots that have variables raised to exponents. If it's even, that's really simple, right? What do you pull out? Well, you just take that exponent and you divide it by 2. When it's an odd exponent, what I would do is take x squared. You know you're going to have 1 left over underneath the radical. How many do you pull out? You go 1 number down. So I would go x squared for this x cubed, and then you half that. So let's look at example number 5. So it's the square root of 28x squared y cubed. The first thing I would do is simplify the square root of 28. So what's the biggest perfect square that goes into 28? 4, just like we did in examples 1 and 2. 4 times what? 4 times 7. What is the square root of 4? It's 2. So this simplifies to 2 square roots of 7. So now we're going to look at these variables and their exponents. So the first thing is x squared. I have 2 of something, I can pull 1 out. So on the outside of my radical, I'm going to have a 2 and I'm going to have an x. And if you need to draw it out like this over here, like we did, and then circle, x times x and y times y, if you need to circle those, arrow out, I would totally do that. It really helps some students to see it visually like that. So now let's look at y cubed. I know I'm going to have 1 left over underneath the radical. I know because that exponent is odd. The question is, how many can I pull out? Okay, so what I'm going to do is draw my little radical symbol here. I'm going to put a 7 there, and I know I'm going to have a y left over. So what I would do is instead of y cubed, go y squared, 1 less, and then take half of that. That means divide it by 2, right? So 2 divided by 2 is 1, so you're going to take 1 out, and that's my answer. If you visually want to see this, it will look like this. X times x times y times y times y. X times x, I can pull 1 out. Y times y, I can pull 1 out. That's how I got the x, and that's how I got the y. But this is the y that stayed underneath the radical. Let's look at number 6. The square root of 75, a to the 5th, b to the 8th, times c. So the first thing I want to do is simplify the square root of 75. What's the biggest square root that goes into 75? 25. Square root of 25 times the square root of 3. What is the square root of 25? It's 5. So this simplifies to 5 root 3. So now let's look at each of these exponents. So a raised to the power of 5. Because it's odd, I know I'm going to have 1 left over underneath my radical. 8 is even, so I can just half that. See? Well, if there's no exponent, it's just a 1, right? It's odd, so we're just going to leave it there. We're not going to have enough. So here's what it's going to look like. 5 is outside of the radical. A to the 5th, I'm going to go ahead and draw my radical and put a 3 there, okay? A to the 5th, I know I'm going to have an A left over, so I'm going to put it there. So now I've got A to the 4th. I take half of it, right? Which is 2. 4 divided by 2 is 2. So I'm going to have an A squared. And again, if you want to draw that out, A times A times A times A times A. I've got an A, I can pull out. I've got another A, I can pull out. And then I've got this one that's left over underneath the radical. That's why I have A squared outside of the radical, A left underneath. Then B raised to the power of 8. Well, 8 divided by 2 is 4. So I've got B raised to the power of 4. And then I've got 3A underneath my radical, and we can't forget that C, right? We couldn't do anything with it. It just stays C. We didn't have enough to pull out, okay? So there's your answer. Let me put a box around it. And let's move on to examples 7 and 8, where we're multiplying radicals. So the rule is when you are multiplying radicals that have the same root, so this could be a square root, this could be a cube root, this could be a fourth root, you can rewrite it as this, where you just multiply the numbers that are underneath the radicals. Those are called radicands. So I can just rewrite it, which I actually did whenever, for example, the square root of 28, I rewrote that as the square root of 4 times the square root of 7. So I was just going in reverse. So we're going to do the reverse of what we did. The square root of 12 times the square root of 5 on number 7. Well, that's the same thing as the square root of 12 times 5. What is 12 times 5? It's 60. So now I've got the square root of 60. And we can break that down. How can we break that down? What's the biggest perfect square that goes into 60? 4. So I can rewrite it as the square root of 4 times the square root of 15. What is the square root of 4? It's 2. So that's 2 root 15, or 2 square roots of 15. And there's your answer. Let's move on to number 8. You can always simplify before you multiply. Okay, so what I could do, I can see that the square, I can do it just how I did it, right? 8 times 5, that's 40, the square root of 40, and then I can break that down. But what I'm going to show you is you can simplify before you multiply. So the square root of 8, the biggest perfect square that goes into 8 is 4. I can rewrite that as square root of 4 times square root of 2, which is 2 square roots of 2 times the square root of 5. And the reason I want to show you that is because what you do, you multiply the numbers in front of the radical together, which obviously if nothing is there, it's assumed 1, and then you multiply the radicands together. So 2 times, this would be 1, is 2, and then 2 times 5 is 10. So 2 root 10, and there's your answer. And if you would have done this, you would have seen that 8 times 5, that's the square root of 40, and that would break down into the square root of 4 times the square root of 10, which is 2 root 10. So you would have gotten the same answer if you did that problem the same way we did number 7. So let's move on to dividing radicals and rationalizing the denominator. So when I'm dividing radicals, for example, again, these roots are the same. So let's say the square root of a number divided by the square root of a number. I can rewrite it as the square root of the top number divided by the bottom number. But right here, this is really important in algebra. You cannot leave a radical in the denominator. That's not considered simplest form. So remember that we always want to put things in simplest form. You've been doing this since, 3rd grade when you simplified 2/4 to 1/2, right? Simple is better. So in upper level math, a radical in the denominator is not considered simple. So how do we get rid of it? How do we rewrite this expression so that we remove that radical from the denominator? We use a process called rationalizing the denominator. So here's what you do. In number 9, this is 6 divided by the square root of 5. What I'm going to do is I'm going to multiply this fraction times the square root of 5 over the square root of 5. Now, why would I do that? Well, for one thing, I'm not changing the value of 6 divided by the square root of 5, because what am I really multiplying that fraction by? Anything divided by itself is just 1, right? So I'm just multiplying it by 1. But let's see what I get when I multiply this fraction by 1. 6 times the square root of 5, well, we just did multiplying up top. That's just 6 root 5. But then in my denominator, the square root of 5 times the square root of 5, well, that's the square root of 5 squared. If I take the square root of 5 and I square it, the square root and the square cancel each other out. So what I have effectively done here is I've got 6 root 5 divided by 5. And that is considered way simpler than dividing 6 by the square root of 5, because that's an irrational number and it's just more difficult to do that. So this is 6 root 5 divided by 5, and that is my answer. We're going to do that exact same process on number 10. So I have 25 divided by the square root of 10. So what am I going to multiply everything by to get rid of that denominator, or that radical in the denominator? I'm going to multiply everything by the square root of 10. And I get 25 root 10 over, and let's go ahead and say it, or write it this way. Square root of 10 times the square root of 10, well, that's just 10. So you'll see a lot of students skip from this step to this step, because what do they see? They see that we just took that radical and the radicand, what's on everything in the denominator, moved it to the top and removed the radical in the bottom. What you have to remember at this point is 25 and 10. I can still simplify that. I can divide both numbers by 5. 25 divided by 5 is 5. 10 divided by 5 is 2. So I can rewrite this and put it in an even simpler form as 5 times the square root of 10 divided by 2. And that is my answer. Let's move on to 11 and 12. So 11 and 12 are examples where we have a number in front of the radical. So really, 15 divided by 3 root 5, all I really want to remove is the square root of 5. So that is going to be what I multiply the numerator and the denominator by to get rid of that. So I'm going to rewrite it, multiply across, right? When you're multiplying fractions, ain't no problem. It's top times top and the bottom times the bottom. So that's how I get 15 times the square root of 5. I get 15 root 5 divided by, in the denominator, I now have 3 times the square root of 5 times the square root of 5, which is just 3 times 5, right? Because the square root of 5 times the square root of 5 is just 5. Okay, we remove that square root, or that radical. So now I'm going to rewrite it again. 15 root 5 divided by 3 times 5 is 15. So what can I do at this point? I can simplify the 15s. 15 over 15 is just 1, which is 1 times the square root of 5. Well, that's just the square root of 5. Over 1, well, I can just write it as the square root of 5. So let's move on to number 12. In example number 12, we have 8 divided by 4 root 6. So you can solve this the exact same way we just solved number 11, or you could simplify it beforehand if you want. For example, 8 divided by 4 is the same thing as 2 over 1. So I can simplify what's in front of the radical and my numerator. And I can rewrite it as 2 over the square root of 6. Again, you don't have to do this, but you can simplify before you divide if you want. just like we did when we were multiplying radicals. So what do I need to multiply by to get rid of the radical in my denominator? The square root of 6 over the square root of 6. So what does that effectively do? In my numerator, I now have 2 root 6 over 6, right? That removed that radical from the denominator. We have successfully rationalized the denominator, but now we're not done. What do we need to do? We need to simplify it. 2 over 6, that's just a fraction, right? How can I simplify that? Divide by 2. I get 1 over 3. So I can rewrite this as the square root of 6 over 3, and that's my answer. And you would have gotten that if you just didn't simplify 8 over 4 first, right? If you just multiplied by the square root of 6 and you did all that, you could simplify it at the very end and you would get the same answer. So now we're going to rationalize the denominator of a cubed root. So this is a little more involved. It's sometimes a little more confusing for students. So on number 13, if I have 4 divided by the cube root of 5, again, if I'm going to remove that radical, how many 5s do I need under here to get rid of it? I need 3 of them. Right now, I only have 1. How many more do I need? I need 2 more. So I'm going to multiply this by how many more I need to get rid of that radical, which isn't just the cube root of 5. It's the cube root of 5 squared, right? I need 2 more. I need 2 more. That's 5 squared. If I'm going to multiply this fraction by something but keep the same value of it, I need to multiply it by 1, right? It's just, what does 1 look like? In this case, it's the cube root of 5 squared. So now let's rewrite it. Now I have 4 times the cube root of 5 squared, which I'm going to go ahead and write as 25, but it's because a lot of students want to go, but wait, the cube root of 25 is 5. No, the square root of 25 is 5. The cube root of 25, I can't break that down. Over, now, because I now have the cube root of 5 times 5 times 5, that I've got 3 of something, I can pull 1 out, right? So that removes that radical, and I'm just left with 5. And that is my answer. So, looking at number 14, if we look at it from the same perspective, then I would need to multiply the numerator and denominator by 4 squared, right? But what if I rewrote it like this? What if I rewrote this expression as 7 over the cube root of, what's another way that I can write 4? I could write it as 2 squared, right? So now, is it the same value? It sure is, because 2 squared is 4, right? So I still have 7 divided by the cube root of 4. So it's the same value. But now I have the cube root of 2 times 2. And if I want to remove that radical, how many more 2's do I need? I need 1 more. So now, in this case, I'm just going to multiply it by the cube root of 2. What I do to the bottom, I've got to do to the top, so the cube root of 2. And now I have 3 2's, and I can pull 1 out. So this particular answer is 7 times the cube root of 2 over 2. And that is considered simplest form. Let's move on to our very last part of today's very long notes, and it's using conjugates to rationalize the denominator. So let's refer back to our factoring, when we were factoring and we factored a difference of squares. So if I have, for example, 2 binomials with the same terms, but one is plus and one is minus, what happens? Well, those 2 middle terms end up canceling, right? And I'm left with a squared minus a difference of b squared. So if I look at that from a radical perspective, if I have the square root of a plus the square root of b times the square root of a minus the square root of b, then I'll end up getting the square root of a squared, which is right here, minus, there's my difference, the square root of b squared. So if I were to simplify, remember the square root of something squared, what happens to that radical? The radical and the exponent, they cancel each other out, right? So I'm left with, like these two things will cancel each other out. These two things cancel each other out, and I'm just left with a minus b. So in 15 and 16, you have a binomial in your denominator with radical. It contains radicals. So how do you get rid of those radicals? We're going to multiply by the conjugate. So we're going to multiply this binomial times what will get rid of those radicals, which would be the square root of 5 minus the square root of 2. And that is known as its conjugate. One's plus, one's minus. It's that simple, right? But again, we're making this, we're going to make this fraction have the same value. So what we do to the bottom, we have to do to the top. And I get the square root of 5 minus the square root of 2. So we're not changing the value of it. So in this case now, in our numerator, we're still multiplying across. I just have 3 times the square root of 5 minus the square root of 2. And what I want to show you in your denominator, you don't have to write this every time, but I want to show you kind of what happens if I were to FOIL these two binomials. Okay, so the square root of 5, the first terms, right? Square root of 5 times square root of 5, well, that's the square root of 5 squared. The outside terms, well, the square root of 5 times square root of negative, the negative root 2. So, or I wouldn't say the square root of negative 2. I almost said that. So 5 times the negative root of 2, which would be minus square root of 10. The inside terms, the square root of 2 times the square root of 5 would be plus the square root of 10. And then the last terms, square root of 2 times the negative square root of 2, which would be the negative square root of 4, but I'm just going to write negative square root of 2 squared. Okay? So what do I have here? What happens whenever I multiply these two binomials together where I've got the same terms, one's plus, one's minus? These two inner terms cancel, and I'm left with the square root of 5 squared minus the square root of 2 squared. And those square roots and the exponents cancel each other out. So I'm going to rewrite that on this example. 3 times the square root of 5 minus the square root of 2 over 5 minus 2, which is 3. And I'm just going to rewrite it because I'm writing every single thing. You can see every single step. Over 3. And then what can I simplify? The 3's. So I can cancel the 3's, and I'm just left with the square root of 5 minus the square root of 2, or root 5 minus root 2, and that's your answer. Let's move on to our last and final example, problem number 16. Lots of examples. So I have 10 divided by the square root of 7 minus the square root of 15. So I'm going to multiply it by its conjugate to get rid of the radicals in the denominator. The conjugate of the square root of 7 minus the square root of 15 is the square root of 7 plus the square root of 15. And what I do to the bottom, I have to do to the top. And now let's rewrite this. In our numerator, we have 10 times root 7 plus root 15 divided by what ends up happening. Again, those terms lose their radicals, and I'm going to have subtraction, right? So it's just going to be 7 minus 15. Think of your difference of squares. So now when I rewrite this, I've got 10 times the square root of 7, or root 7, plus root 15, over 7 minus 15 is negative 8. And now I can simplify the 10 and the 8. Or negative 8. So I can divide by 2. 10 divided by 2 is 5. 8 divided by 2 is 4. So I'm going to rewrite that as 5 times root 7 plus root 15 over negative 4. And you can put a negative out in front if you want. It's going to be the same value. But there is my answer, and that concludes your very long notes today over simplifying, multiplying, and dividing radical expressions. I hope it was helpful.